dry cast. But this sort of is another graph that shows that by the year 2015, the pools are going to be maxing out, even with this high-density configuration. I mentioned decay heat. This is a very, very important issue, as I said. From the point of view of safety in terms of spent fuel storage, the loss of water is a very serious matter for spent fuel. The National Academy of Sciences basically, I think, came up with a good explanation of what happens when you lose water and it heats up. The zirconium basically will spontaneously combust at somewhere around 800 degrees centigrade. They said it is strongly exothermic. The result could be a runaway oxidation, referred to as a zirconium cladding fire, that proceeds as a burn front, e.g. as seen in a forest fire or fireworks sparkler. This is sort of what a spent fuel fire would look like. And it's largely due to the enormous decay heat and the reactivity of zirconium. In 2003, several colleagues and I were stricken from the Christmas card lists of a lot of people in the nuclear industry. When we published a paper basically raising the concern about the vulnerabilities of spent fuel pools, particularly to acts of terror and other events like earthquakes. And what we did is we took the literature of the last 25, 30 years of nuclear spent fuel pool safety and took it to its logical extreme. And this is what happened is that, of course, the nuclear industry, the Nuclear Regulatory Commission was not happy with us and issued quite a few statements and papers, etc., in rebuttal, and this prompted the U.S. Congress to ask the National Academy of Sciences to sort this out. We then went before a special panel, and this is what one of my colleagues, Frank von Hippel, presented to them as to what we're looking at in a sort of a generic sense of what might happen if you have a pool fire. What this graph basically says, you could have a pool fire at a commercial nuclear power plant in the United States could be as large as 60 times greater than essentially the cordon sanitaire around Chernobyl. We also provided some damage estimates, just the standard damage estimates that the industry uses to give you an idea of what the monetary possible carcinogenic estimates would be, just using the standard formulas that the Nuclear Regulatory Commission uses. This is what it looks like. You know, this kind of accident, such as Chernobyl, similar to Fukushima, deal body blows to entire nations. They are highly destabilizing to the stability of an entire country when you have events like this happen. The National Academy came back a year later, and this is what they had to say. They basically agreed with us. They basically pointed out that these pools are particularly vulnerable to terrorist attacks, and that these fires could be quite significant. The Nuclear Regulatory Commission essentially flipped the bird and really did nothing to acknowledge the importance of this study, as far as I can tell. You've heard yesterday from David Lochbaum that the Nuclear Regulatory Commission has made the statement that the dangers of dry versus wet storage are the same. This happens to be a chart that I took out of a document by the Nuclear Regulatory Commission Emergency Operations Center. As a recovering bureaucrat of the Department of Energy, I'm familiar with operating in parallel universes. And this is the other universe. This is the Emergency Planning Center. This is the data that they're using to do desktop planning and their exercises. This is based on the Rascal code model, and this gives you an idea. And this is the source. It's on the internet if you wanted to bother to find out. And this involves a reactor, interestingly enough, called the San Onofre Nuclear Generating Station. And it's a workbook. It explains, how to use this code, and it gives you problems. And it says, well, You've just received a phone call from the staff at San Onofre, and they've had an earthquake. The roof is gone. The pool is draining. They've put a full fresh core load in there, and the tops are already being exposed. What do you do? How do you ascertain what to expect? And this is what the answer was. The amount of radioactivity that would be released in the environment would be 86 million curies. About 26 million would be cesium-137. Your doses within 1 to 10 miles would essentially be prompt lethal to killing half of the people, or giving the LD50 dose, 450 to 5,200 rems. These are all what you would call ablation doses, destruction of the thyroid, period, for people within a 10-mile radius. This, again, is the same report. This is interesting because it shows you what's called the fraction, release fraction from a cladding fire. It's at the very end of this one here. 100% of the noble gases get out. About 70% of the halogens, which are your radioactive iodine, 30% of your radiocesium gets out, and then you see these smaller fractions estimated to be released here. And these here are really the biggies when you have a large radiation release, and we've talked about this before. And I think that these noble gases here have been entirely dismissed without proper justification, especially when you're talking about weather conditions that would create immersion doses and very large exposures. And the halogens we've known about, radioiodine and the cesium. But this is the NRC's parallel universe here. This is the inside versus what they say to the outside. They also gave an exercise about, well, a terrorist has basically put a shape charge on a cask at the Prairie Island nuclear station. And how do you figure out what the release will be and what the doses would be? Well, this is the comparison. A cask would release as much as 34,000 curies of radioactivity. By the way, this is on a logarithmic scale, because otherwise I couldn't present it that way. And versus 36 megacuries. Your doses, everybody within a 10-mile radius essentially would have a near lethal, if not a lethal, prompt lethal dose. Your off-site doses, now at Prairie Island, as some of you might know, that reactor is Chikanjal with a small Indian tribe. So these are their dose estimates. 1.9 to 4 rem total effective dose equivalent, 0.1 to 0.2 rems. I'm sorry for the typo here. I was busy doing this yesterday. For thyroid. Your thyroid doses, your total effective dose equivalent are just off the chart. I may add, by the way, do you know what's in the 10-mile radius of the San Onofre nuclear power station? The world's largest United States Marine Corps base, Camp Pendleton. And that within that 10-mile radius are 64,000 people who are Marines and support people. And I'm curious whether anybody has thought about what this means to our national security. What this means, has anyone bothered to call up the base commander and say, are you aware of this? Are you ready for this if something like this were to happen? Probably not. A lot has been written, said about Fukushima. What I find interesting about certain things are things that are usually not said. And what I found to be one of the most interesting lessons that I gained from the Fukushima disaster is that they had 9 casks at the site, and they were unscathed by the earthquake and the tsunami and all the other aftermath. That's a very important finding. Very important finding. We recommended in 2003 that we return these spent fuel pools to their original purpose, which is for temporary storage for a 5-year period to allow decay heat to move them. And we suggested that they thin out these pools, and restore them to original use and place the remainder into dry hardened storage. We estimated it would cost about $3.5 billion to $7 billion. It would take about 10 years. The Electric Power Research Institute recently came out with a study and said it would be about $3.9 billion, and they said it would mean a lot of reactor downtime and they would not make a lot of money as they are. I believe they treat these reactors like ATM machines. If the consumer were to pay for this, this is how much it would cost to do this. And we're looking at an enormous reduction in the potential consequences and risks and hazards of doing this. Now, these are the types of spent fuel casks. The one on the right, the Castor, I consider to be the Cadillac or the Mercedes. The Holtec, I consider to be the Geo. One thing we have to keep in mind right now is that we are stuck. The whole framework for the disposal of high-level radioactive waste has collapsed in this country. The Yucca Mountain site has been pulled off the table. The Nuclear Regulatory Commission's waste confidence rule, in other words, their rule that says we can jam as much spent fuel as possible into these pools, has been rejected by a federal court, largely on the grounds that their assumptions about the consequences of spent fuel fires did not pass the LAF test. And so they are now embarked on a very time-consuming environmental impact statement. As I said, the maximum high-density spent fuel pools are going to reach their maximum storage by 2015. The other thing to keep in mind is that we have an abundance of a large and long-term abundance of natural gas, which is making these older single-unit reactors more and more vulnerable economically. This is putting more pressure on this industry, who are much more economically motivated than they are with respect to waste management. And we also have to keep in mind that we have large amounts of defense high-level radioactive waste that are stranded. The recommendations of the Blue Ribbon Commission, they are the same we've heard before, except somebody else ought to do it other than the Energy Department. And I won't get into the reasons, but the bottom line is that these recommendations are going to take many, many decades if they are actually implemented, and before any major changes. Just a brief word about military high-level radioactive waste. We have about 100 million gallons in tanks that are larger than most state capitol domes. Roughly a third of them have leaked. After 30 years, we've spent about $120 billion trying to stabilize them, and we've been able to stabilize about 11% of the radioactivity. This is a matter of very high national concern and priority, because we're talking about protecting streams like the Columbia River, the Savannah River, the drinking water supply of the southeastern coastal plain of the United States. These are very important issues. My conclusion: we've been looking for a place to dispose of these wastes for actually close to 50 years now, close to 60 years rather. But one thing I think we need to understand and have to come to terms with is that some of the largest concentrations of radioactivity on the planet are going to remain in storage at U.S. reactors. I think this is something you have to think about very seriously for the indefinite future. I think that we have put the disposal cart before the storage horse. We've always thought that we would find a place, and there was no need to take the extraordinary steps that nations like Germany have done to protect their spent fuel, and I think we need a national policy that basically takes the hazards of these pools, reduces the hazards, and establishes a safe storage policy before we start to find a geologic repository. Storage and stabilization of military high-level waste should also be national priorities. This is all going to be quite expensive. And as I said, the costs of fixing America's high-level radioactive waste storage vulnerabilities are high. The costs of doing too little are incalculable. Thank you.